what are aquifers? They are water saturated. And in this class, I'll just assume that SW is equal to 1, meaning there's no oil or gas in the aquifer. Porous rock. Now, a lot of times we hear about shallow aquifers, right? Maybe a few hundred feet below the Earth's surface. People drill wells for that, for fresh water and things like that. That's not really what we're talking about. We're usually talking about aquifers that are deeper, although they're analogous, they're very similar. And what we're talking about is aquifers often surround a hydrocarbon, so oil and gas reservoir. Right, so how we're going to conceptually view this is that we have our reservoir, and I'll draw a little well bore in between there. So this has got a radius of RW, but the reservoir has a radius of RE. That reservoir is going to have water, oil, and gas potentially. Okay, so might have only oil or only gas, but it could have both. But it likely has a little bit of water in there as well. We call that irreducible or connate water. That's the reservoir, and then in the outer region, we're going to have our aquifer, and SW is equal to 1, and we'll say the radius is RA, so the radius of the aquifer. So that's how we conceptually view it. Now, of course, most, or I should say no reservoir is perfectly cylinder, no aquifer is a perfect cylinder, but nonetheless, this is how we conceptually view these models, and it's fairly easy to correct for the irregular geometries. So one thing is that we don't always have a perfect circle, or it's completely over there. It might be just part of that, a fraction of that, and I'm going to call this angle theta. And we often use this factor F, which is theta divided by 360 degrees. Oh, yep. So F is theta divided by 360 degrees. So if theta were 360, so a full circle, that would be 1. And if theta is less than 360, then you'd have F of less than 1. Now, I mentioned that these reservoirs and aquifers are not perfect circles. That's okay. Okay, what we usually have is we have an area, and then we transform it to an effective circle or effective radius. So the effective radius of the reservoir is the square root of A res divided by pi F. Okay, so because we know that area is equal to pi r squared of a circle. So you correct with the F, and then if you want to find the radius, you take the square root of the area of the reservoir, which would be given by a geological map or something, divided by pi F. And then likewise, for the radius of the aquifer, you have the area of the aquifer divided by pi F. Okay. And then if you wanted to calculate how much water is in the aquifer, well, that would be, we're going to call that WI. Probably going to measure it in barrels. And what is that? That's going to be the volume of the outer cylinder minus the volume of the inner cylinder. So the outer cylinder is the aquifer, the inner cylinder is the reservoir. So what that is going to be pi F, because it might not be a perfect circle or perfect cylinder, the radius of the aquifer squared minus the radius of the reservoir squared times porosity times the thickness, right? Because what's the volume of a cylinder? It's pi r squared h. So we have pi r squared h, but we've got they're concentric cylinders. So it's the outer cylinder minus the inner cylinder. That's why we have RA squared minus RE squared. We correct for the fact that it might not be a perfect cylinder. It might be only part of it. So we have the F factor. And then the water is obviously only in the porous part, so we include the porosity phi. So WI would tell us, if you put it in the right units, how many barrels of water are in the aquifer. Now, it's important to remember that every drop of water in the aquifer does not encroach the reservoir. In fact, only a percent of it will. And so don't be confused and calculate WI and think that that's how much water is going to encroach, because that number should be significantly less. We return to the material balance equation. I'm going to abbreviate that MBE. You learned this in Reservoir 1. If you've forgotten a little bit about it, then maybe you will watch the video I made, which will be a good reminder of that. So material balance, and one way to write it is like this. Okay, so that's a simple way to write it. So GFGI is the gas in the gaseous phase, NFOI is the oil in the oleic phase initially in both cases. So that's the initial amount there. EGWF and EOWF are effectively PVT properties. They're a combination of formation volume factor and solution gas ratio and whatnot. F is a function of the amount of fluids produced. So you measure that at the surface, and you'll get that with time. So it's related to the amount of oil produced, water produced, gas produced. There's an equation for F, but I'm just going to leave it over there. And I should point out that that changes with time, right? So you produce more fluids with time. So F is increasing with time. Then WE is the water that encroaches the reservoir. So it's the cumulative amount of water that's encroached at any given time. So that's got units of barrels, and so that's going to also be a function of time in general. So WE increases with time usually. So you have a little bit of water encroach early on, and then as time goes on, you'll have more and more encroach. GFGI and NFOI are constants. So WE is what we're interested in here. It's the cumulative water influx. And what we do is we have models to predict WE, right? So what we want is to come up with a mathematical model that tells us how much water is going to come into the reservoir in the future. And then we can use that to help us determine how much oil and gas we'll produce in the future. That's really our job as reservoir engineers, is to figure out how much oil and gas is in place, and then how quickly we can get it out, and then ultimately what the economic value of that is. So the first model we discussed last time was a small pot aquifer. Okay, and I'd like to point out that it's simple but least accurate. Okay. It's really only accurate if you have a small aquifer. That's why we call it a small pot aquifer. And the key thing is there's no time dependence. So it doesn't tell us how WE increases with time. What it really tells us is the ultimate amount of water that will encroach. So if you were to wait long enough, a long period of time, how much would come in. And the equation that we learned, WE is equal to WI, which is, again, the barrels of water in the aquifer, times the compressibility, times the pressure difference. So PI is the initial pressure. Okay, you can measure that with a pressure gauge in the well, or you can estimate it from hydrostatic head. P is the pressure in the reservoir or the reservoir aquifer interface. I think on the slides I used P sub A, but I don't really like that because that implies it's the aquifer pressure, and it's really more the interface of the aquifer reservoir, even the reservoir pressure. CT is the total compressibility. So that's the compressibility of the water plus the rock. There's no oil or gas compressibility because there is no oil or gas in the aquifer. So this was the formula that we had. So if you know all those things, you can calculate WE. Again, there's no time dependence in that equation. There was a dimensionless form. which was WED, is equal to RED squared minus 1 divided by 2. As engineers, we like to use the dimensionless equations because those apply regardless of the conditions that we have. And if we want to make plots or tables or things like that, then we can use a generic equation, and then we can calculate WED and RED much like we did on Friday in our example problem. And so, as a reminder, RED is a ratio of the aquifer radius, the outer radius, divided by the reservoir radius, RE. WED is a dimensionless water influx, so it would be WE over U PI minus P. And then U is, we call that the, so this is got units of barrels per PSI, and it's 2 pi F RE squared H phi CT. And if we want that in barrels per PSI, we can use a conversion factor, which is 1.19 F RE squared H phi CT. This would give us barrels per PSI, where I use feet for the radius and the thickness, and I use, yeah, let me just do that. So so maybe you can see that a little bit better. I've introduced this 1.19, and let me show you where that 1.19 comes from. So 2 pi, that's this, divided by 5.61. There's 5.61 barrel cubic feet in a barrel. That's equal to 1.19. So that's why there's no 2 pi in there, and that's why even though we use feet for radius and thickness, the final units are in barrels per PSI. So if you want, and you want to avoid doing any unit conversions, you can just use that, okay? So, and you can double check that, but 2 times 3.14 divided by 5.61 should be 1.19. So these are the value used in that equation. Here's your U. Okay, so that is the small pot aquifer. But what we did last time, what we started to do last time, is talk about a different model. And that was the, and I will continue to mispronounce this, but the Schilithius steady state model. And it includes time dependence, right? So that's an advantage over the small pot aquifer, is that it does include time dependence. And the model proposed was that the change in cumulative recovery with time, so you can think of this as a water rate, right? How much water, so like barrels per day, so it's a rate, is equal to some constant K prime times Pi minus P. Okay. So we know what WE and T for time is. Pi is initial pressure, P is the reservoir pressure, and then we have this new constant which we're going to call the water influx constant. Which has got units of barrels per PSI per day, right? And do not confuse that with permeability. I know we use K for permeability a lot. That's why we put a prime on there to distinguish it from permeability. They're not related at all, okay? So this is the equation, and so how do we use it? How do we use it to determine WE? Well, the first thing is we need K prime. So the idea is first use past production data to determine K prime. Okay, so maybe we've been producing this field for a long time, or maybe we bought this field from another company And they've been producing it for a long time, and they've published their data and shared it with us. So we have past production data, and you can calculate K prime equal to WE dt divided by the initial pressure minus the reservoir pressure. So we'll have the initial pressure. We'll have the pressure of the reservoir with time because there would have been pressure gauges in the wellbore. And I'll explain in just a moment how we calculate dWE dt. Part B. So once we do that, we estimate future water influx. That's what we care about, right? Okay, I mean the past has already happened. What we really want to do is be able to figure out what's going to happen in the future. How much water is going to encroach it, then we can use it to figure out how much oil and gas will produce. Then we can use it to make decisions like, should we drill more wells? Should we start a water flood? Should we sell the reservoir? Things like that. So again, using this equation, this is a derivative, so you can integrate it. So WE is a function of T, is the integral from 0 to T of K prime Pi minus P dt. And things like the reservoir pressure P will change with time. You might be able to make some estimations or predictions about it. And then this integral may not be able to be done analytically, so you'll have to use numerical approaches like the trapezoidal rule. So going back to over here, how to predict K prime. Okay. Well, we're going to use the material balance equation, which I introduced earlier. Now, if you have an undersaturated reservoir, undersaturated means that we only have an oleic phase and you don't have a gaseous phase. You'll have gas dissolved in the oleic phase, but you won't have a gaseous phase. Then the MBE reduces to NEOWF plus WE is equal to F, which is BONP plus WP BW. So if you don't quite see where this comes from, then try to work it out yourself. So start with the most general form of the material balance equation and then reduce it to this. But the point is that there is no free gas phase. So GFGI is 0. NFOI is just N because there's no oil in the gaseous phase. So N is the original oil in place. WE is again the water produced, and the productions terms do this. So BO and BW are formation volume factors. NP and WP are the cumulative amount of oil and water produced, which of course you're going to measure at the surface. Okay. You can take the derivative of these, and you get EOWF dN dt plus WE dt is equal to BO QO plus BW QW. Why is that? Well, NP is the oil produced. Change in oil produced with time is the oil rate. Change in water, cumulative water produced with respect to time is the water rate. You'll have those measured as well. N is the original oil in place. It is a constant, so it doesn't change with time. That means that whole term goes to 0. Okay. I'm going to do an example problem. Okay. So somebody says, can you show the paper again, please? So let me put that right back up before I move back on. So maybe this is what, okay, so I'll give you a quick second to finish writing that out. This is a relatively simple example, is that we have a field with properties and production data given in table 1 right here, maintaining a constant pressure above the bubble point, so that means we're undersaturated, as a result of an aquifer influx support. Use these data to determine the Schilithius steady state aquifer influx constant, That's K prime. Okay, so we know that dWe dt is equal to BOQO plus BWQW, right? That was just what we learned there. And I plug those in, what I get is 1.45 reservoir barrels per stock tank barrel. That's BO. QO is 5,000 stock tank barrels per day. Make sure I include my units so that everything matches up. BW is 1.02 reservoir barrels per stock tank barrel. That's here. And then QW is 1,000 stock tank barrels per day. Right. So we're measuring that at the stop. Now, we've got constant rates here. I mean, usually those will change with time, but maybe over a short period of time they're relatively constant. Especially early on, you might be operating your reservoir at constant rate. And so that is going to equal to 8270 reservoir barrels per day. You might want to verify that. Okay. And so it's a rate, so it's reservoir barrels per day. By the way, the fact that we're producing water at a significant rate, 1,000 barrels per day compared to 5,000 barrels per oil, is a sure indication that we probably have an aquifer. Right? We're not injecting water. This isn't a water flood. We're going to learn about that in the future. We're just doing it in primary recovery. And usually during primary recovery, any water that's in the reservoir is irreducible, meaning it doesn't flow. So you're not going to produce very much at all. The fact that we're producing 1,000 tells me that there was an aquifer, it's invading the reservoir and then making its way through to the wellbore. So now that we got dWe dt, I can say that K prime is equal to dWe dt times Pi minus P. So that's 8270 reservoir barrels per day times 3,200 minus 2850 psi. So that gives me 23.63 reservoir barrels per day per psi. And so one thing, maybe I should be more consistent, but I do use RB, reservoir barrels, sort of synonymously with BBL, barrels. They both really mean barrels at reservoir conditions. I'll use stock tank barrels when I mean, at the surface. Those, obviously we know that stock tank barrels and reservoir barrels are different due to a formation volume factor. So that's a simple example. I have one more example. And again, if you missed this, then feel free to go back and look at the video, and I encourage you to do this yourself. But I have another example, and this one is a little bit more challenging. Okay. This one says that a field has a strong water drive, as the PVT and production data show in the two tables below. So we've got some information about compressibilities and initial water saturation, porosity, permeability, and whatnot. And actually this should look really familiar because it's the same table we used for the example problem we did Friday. And that was to use a small pot aquifer. This should be more accurate. And then we have a table of production data. So we have the time, okay, we have the date, and then I put the time in terms of days. We have the pressure of the reservoir, the oil produced, the gas produced, the water produced, and then the formation volume factor of the oil. Formation volume factor of water doesn't look like it's given, but we can assume that it's 1 if we don't know otherwise. Okay, this is a little bit more difficult because what we have is we've got we're not just given a constant oil rate and a constant water rate, but we're given a constant we're given a table of rates. So let me work this problem out. Okay. Let's go back to the material balance equation. This is an undersaturated reservoir. See, how did I know that? How did I know it's an undersaturated reservoir, meaning that there's no gas phase? Well, the initial pressure says that it's 2532 psi, and the bubble point is 737 psi. So we're well above the bubble point, which means that no gas has come out of solution yet at reservoir conditions. So I have an undersaturated reservoir, which means the MBE reduces to this. Okay, before we took the derivative of it, but I'm not going to do that here because I have lots of different data, and the oil rate and the water rate are not constant. I'll blow this up just a little bit for you. And so one thing we need to know is this EOWF. Well, I bet that most of you have forgotten what that is equal to. In fact, I forgot, so I can't blame you for that. But if you go look at your reservoir engineering equation sheet, it'll be on there. And it's approximately equal to BO, the formation volume factor, minus the initial formation volume factor, plus the initial formation volume factor times C capital T times delta P. C capital T is a little different than the lowercase t. It's CF plus CW SWI 1 minus SWI. Okay, and if I put all that in, EOWF is equal to BO, which is going to change with time, minus BOI is given 1.078 times 1 plus 4 times 10 to the minus 6 inverse PSI plus 3 times 10 to the minus 6 inverse PSI. That's the compressibility of water times the initial saturation that was given to us in the table is 0.48 over 1 minus 0.48 times 2532 minus P. And I can rewrite that as BO minus 1.078, 1 plus 2.046 times 10 to the minus 5, 2532 minus P. Now, I didn't put in BO or P because those both change with time. So EOWF is going to change with time. Okay, so I won't, again, if you want to plug in those numbers yourself, if you want to go back to the video and pause it, I think that would be good. So one thing we can do is compute WE with time. So going back to our material balance, WE of T is equal to BO NP plus BW WP minus EOWF times N. Okay, so let's go back to our problem here. Okay, so we were given OOIP, the original oil in place, and that's given in million stock tank barrels. So this is N. Okay, so we got N here. We have data which shows the pressure. So we got P. Okay, and then BO is a function of pressure, and we have BOI. So there's an equation that you can calculate the formation volume factor given the compressibility and the pressure change. So we can calculate EOWF, NP and WP are both given. Oh, I'm sorry. We don't have to calculate BO. It's given as well. So BO is given, so you can calculate EWF. NP, WP, BO is given. BW we can assume is 1. So what I did is, and I can share the raw table with you, but maybe you can do this on your own, is that I made my own table. So this column and this column are given. Those were in there. Then I calculated F, which is BONP plus BWWP. Those were both given. So I calculated F in reservoir barrels, calculated EWF in the equation I gave you. Then I can calculate WE from this equation. So WE is given here. Okay, so I just calculated that in my spreadsheet. Delta P, that's easy to calculate because that's the initial pressure minus the current pressure. So 2532 minus 2503 is 29. And if we want to get dWE dt, it's going to be equal to delta WE times delta T, or WE at the current time minus the WE at the last time. So you see this number here, 4351.9, that's going to equal to this WE minus this one divided by 274 days minus 0 days. 5709 will be 1.172 minus 1.19 times divided by 366 minus 274. So it's a derivative approximation. So now I've got a column dWE dt, and we know that dWE dt is equal to K prime times delta P. So I've got a column for dWE dt, I've got a column for delta P, and if I plot those, and let me blow this up a little bit. So this is dWE dt, this is delta P. I plotted my points, and then I fit a line through it. And I fit a line, I forced it through the origin. There shouldn't be an intercept. So I made the origin 0, and I get this equation here. Y is equal to 150.74. Now it looks like a pretty good fit. It looks like it fits a straight line well. So I get K prime is 150.74 reservoir barrels per day PSI. Okay. And so this example problem is on Canvas, so I encourage you to redo it on your own. Okay, you can go back in the video and check your work, make sure you get the same thing I do, but it would be good to do it on your own. And this was for an undersaturated oil reservoir. It'd be slightly harder, but you could do it for a saturated where you have both oil and gas present.